Hello, let's answer the few questions we have. Sucrose. Description about that. Sucrose is a disaccharide. So we're going to draw a glucose, the normal hexagon, that is for the pyranose ring, right? So based on the previous drawing, it should be 1, 2, 3, 4, 5, 6 carbons like that. And only the third OH is sticking up, right? The number one carbon is the aldo, or it is also called the anomeric. And that's the most reactive carbon in the sugar. Now, let's draw the other part, the other monosaccharide, which is fructose. Now, fructose is flipped. Don't bet on too much on this drawing. This is not the standard drawing. So we flipped fructose and draw it, but there's 6 carbons. 1, 2, 3, 4, 5, 6. Because we flipped, that's why 1 is on your left, right? Now, what's the connection here? The two sugars are connected using its anomeric carbon. So that's why I want to mention the anomeric. The anomeric is number 2. So now what actually happened, these two OHs, number 1 and 2, removed a water molecule in the condensation, in the synthesis, and it combined. So that makes the two monosaccharides to a disaccharide, right? Let's draw it this way. So now we can describe the connectivity between the fructose and glucose. So this is written as glucose, GLU, and it's connected for alpha because it's sticking down from the one carbon, right? The OH, and goes into the second carbon beta. It's actually sticking up. So that's fructose. So that's how we write it. That's the alpha 1 2 beta connection. The only thing is, it's you see the green, the fructose is flipped. Just notice that. Now, that's one way. There are other ways to draw. So this is a good way to know the disaccharide description, alpha 1 2 beta, and also the anomeric carbon 1 for the glucose and 2 for the fructose. Now, if you put the sucrase enzyme, and it's going to add a water molecule across the glycosidic bond between two sugars, the bond is called the glycosidic bond, right? It means the glycose into glycose, sugar into a sugar, right? Okay. Now, if you are synthesizing, you are removing a water molecule, you are making the disaccharide going upward. Basically, the biosynthesis has a little bit of a different path, but the idea, the logic is similar. Now, if you add a water molecule across this bond, so you just put a water molecule and break it as I marked, and you will have the two monomers separated. So that's the digestion with sucrase enzyme. So I don't show the sucrase enzyme, it's a bulky protein, right? Now what you end up with is the monosaccharide sucrose, fructose, right? And fructose still flipped here, so I didn't change. And glucose acid is, right, the normal drawing. And so now we ended up with one glucose, which is in the hexagon shape. We call the pyranose, or we can call yes. When the synthesis occurs, you just remove a water molecule from here, and it goes up, make the disaccharide. Now we came down, which is the digestion, right? So a little bit of labeling here. Um, let's put the yes, 1, 2, 3, 4, 5, 6, and that just to mark the anomeric carbon, which is the blue dot. And if you go to an open chain, so let's say 1, 2, 3, 4, 5, 6, right? So if you go to an open chain, normally you're gonna draw this way. What's the idea? This is a Fisher projection, right? So now remember again, you put third one sticking to the left and everything else is to the right basically. And anomeric carbon is an aldo. So anomeric is number one, it's an aldo. So that's the nature of the glucose and aldo sugars. Now this last chiral center, like I mentioned, it's sticking to the right. So that's a D-dextro. That's this one is called this skeleton is called the D-glucose. The open chain is D-glucose. The ring form, the blue one, is the D-glucopyranose, right? Now we go to the fructose, that's also D-fructose. Now D-fructofuranose, we can open up like this way. Now again, 1, 2, 3, 4, 5, 6 carbons. And again, in the skeleton fructose, third hydroxide is to the left and the fifth one to the right. So that's why it's D-fructose. The skeleton has the second carbon is the anomeric. And it's also a keto group. So it's a 2 keto, 2 anomeric, right? And it's D-fructose because of the fifth hydroxide group is sticking to the right. So that's the LD convention, and where the anomeric, the most reactive one. So that's the thing to understand to describe these two, right? Now pyran ring is simply the hexagon and furan ring is simply the pentagon, right? So that's how kind of the shapes you can memorize. Think about the pentagon, the building, right? Okay. Now what's the next question we have? This is all about descriptions, right? Yes, we have the oxidation and reductions, is it? Yeah. Yeah, so let's draw again a aldo sugar, and when the third one is to the left, that's glucose, D-glucose actually, right? Here's it's a good one to memorize if you're a, pre-med MCAT DAT student. It's better to memorize it. Now, I'm going to do first for the oxidation reduction, I'm going to do the reduction because it's one step done, right? Always. When you study, simple ones finish first, so you feel the completion of studies, right? Okay. Um, so this one can be drawn double bond O, the aldo group. It's better to show it that way. Now, only thing we reduced gaining electron is reduction of that aldo group, aldehyde group into alcohol. The rest stayed the same. See the green? I didn't change anything for the carbon 2 to carbon 6. So just notice what is changed. Now D-glucose actually became glucitol. Now this one is a polyalcohol. I'll explain below that one. Now go to the oxidation. Losing electron is oxidation. Now oxidation with bromine, actually bromine water solvent, but you are oxidizing only the top aldehyde into a carboxylic acid. That's the only change. Rest, keep it as it is. So this one, again, you have the glucose skeleton and you make a carboxylic acid on the anomeric carbon, the most reactive carbon, the number one. So that's that. Now there's another oxidation. You can add nitric acid, and the nitric acid is going to oxidize the two ends, the top one carbon and the sixth carbon. That's the only change, right? So two ends are oxidized. Now that's more stronger oxidizing agent, nitric, compared to bromine. Bromine is milder. That's why this difference, right? Now we also have to label these two, and we do the labeling so you can if you see the names, so you know what type of oxidation has been done, right? Now this one only actually important for the again DAT, MCAT, and the chemistry major folks, and also the biochemistry folks, right? And let's mark these ones. Yes. So when you oxidize the both ends, it's called the glucaric acid. And if you only oxidize one, it's called the gluconic. Just remember, almost looks like a glucose is gluconic. It's some completely different, it's glucaric, right? Now, there's another one. You can actually add periodate. That's a periodic acid. The periodic acid actually oxidizes everything. So you're going to end up with 5 formic acids and one aldehyde. One aldehyde from the bottom, CH2OH, right? If you need details, you can ask me again questions. I'll explain that. Now, the other question we had is about the epimers, right? The confusion about epimers. Epimers are the class of diastereomers. It's within the big umbrella. Epimers are one specific ones, right? I think anomers we explained. Now epimers. Now look at this one again, the D-glucose, the third one to the left, right? And the versus, we draw another sugar. In this sugar, almost the skeleton same, but look at number 2 carbon. The number 2 carbon, the hydroxide group, is sticking to the opposite side. That's the only difference. Right now, one carbon is different. That is called the epimer. One chiral center is different. That's called the epimers. They also in the big umbrella of diastereomers. Right now, again, this one is OH to the right. That's a D. And this skeleton, 1, 2, 3, 4, 5, 6, this skeleton is called the Mannose. Now, the other one, you know, D-glucose, right? So that's how we got the Mannose. Now, we can actually put sodium borohydride or lithium aluminum hydride, and we can do the gaining electrons reduction GER, and you end up with mannitol. So what's the difference? The aldehyde becomes alcohol. That means it's all alcohols. It's called the polyol. And this polyol is very important because you see it in your sugar-free gums, and it's an osmol. It will be used as an IV to pull the water out of cells actually. So in really important scenarios, the IV is given not only dextrose but mannitol, because that pulls out a lot of water from the cell, so you can reduce the pressure, right? Okay, we have another scenario. Let's say, yes, oxidation. So we can, yeah, oxidations we have done, and let's look at the Tollens and the Fehlings again. So we actually discussed in last time too about it, right? Now, here the Tollens and Fehlings is, Tollens is silver mirror, and Fehlings is red copper precipitate. It's actually copper oxide, right? Copper 1 oxide, precise name, but it's a red precipitate. So what's happening here? The D-glucose molecule, the D-glucose molecule's aldehyde becomes Cu, right? That's carboxylic. Now that's an oxidation. Losing electron is oxidation. But when there's some oxidation happening, there should be a reduction happening. It's hand in hand. So you do the Leo, there is a GER. Who is GER? Silver plus gets an electron, becomes silver metal. That's silver mirror. That's how we make the silver mirror. Now this is an ammonia silver complex. If you really need the reagents, you can find out, but the logic is more important, the theory, right? And the failings is you have copper 2 plus blue solution, and it's going to turn into, by the gaining electron of reduction, it will be copper 1 oxide, which is red precipitate.